So now again, we're continuing in chapter 10 on correlation and regression. Now we're on 10.2. We'll go through this in two different parts. So today is part 1 of 10.2. And as a reminder, we went through correlation in 10.1. In 10.2, we're going through regression. Then after that, we only have one more section left for the entire semester. So let's first go through the key concepts of 10.2. So we'll take a scatter plot that has paired sample data. We'll add a regression line to it so we can get the equation for that regression line. The equation we find will be a straight line. So if you remember y equals mx plus b, we'll work with that today in 10.2. The equation for our line of best fit from sample data from a scatter plot will be called a regression equation. So we'll go through a regression equation as well as the regression line. Then later in 10.2, we'll discuss marginal changes, influential points, and residual plots, and how those are tools for analyzing correlation and regression results from a scatter plot where we've added a straight line trend line. Let's cover some definitions now. So a regression line is our first concept. Given a collection of paired sample data, like we see here, that were made into a scatter plot, the regression line, or called the line of best fit, or the least squares line, is the straight line that best fits the scatter plot of the data. So for example, we'd have our X data and our Y data, and we plot all of this in a scatter plot. Then we have Excel add this trend line for us, and that's our regression line. And remember in chapter 10, we're working with straight line patterns or linear correlations or regressions. So this line here is going to be a linear line, and it will have a linear equation for its slope and y-intercept. So this is our regression line. It can be described by this regression equation. Now you may have seen this before as y equals mx plus b. This looks a little bit different, but it's the same thing, where y equals b plus mx. Where again, this is our y-intercept, and this is our slope, this is our independent variable, this is our dependent variable. So we have our regression line, we have our regression equation. This is how we algebraically represent the equation for our regression line. Ultimately, this equation helps us connect our X data to our Y data, corresponding to a y-intercept and a slope. So again, it's this relationship between our X data and our Y data. Most commonly, you've probably heard of our X data as the independent variable. It can also be called the explanatory variable or the predictor variable. And Y hat here, you've probably heard as our dependent variable. It can also be called this response variable. So Y is dependent on X, or Y responds to our X data. Most commonly, you'll hear X as the independent variable and Y hat as the dependent variable. Now you may be used to saying Y here rather than Y hat, but it's essentially the same thing. So why do we call this Y hat instead of Y? Well, we recognize Y as our dependent variable. Then we remember that the symbol notation over certain variables indicates that we're dealing with statistics rather than parameters. So we say Y hat rather than Y because Y hat is a statistical designation of an estimated value. This is as opposed to this variable being for a population parameter. So overall, this regression equation, y hat is equal to b naught, or the y-intercept, plus b1, or the slope, times x. We'll talk more about this symbol notation on the next slide. Now let's go through some more details of finding the equation of the regression line. What would the objective be here? Well, as you may guess, it's to find the equation of a regression line. Now, more on this notation for the equation of a regression line. We saw on the last slide for a statistic, not a population parameter, that we have this y hat is equal to b naught plus b1 times x. That makes this b1 the symbol for our slope. That makes b naught the symbol for our y-intercept. Now, notice the difference as we go from a sample statistic to a population parameter. We call this symbol here beta, so beta naught for a population parameter is our y-intercept. Where beta 1 is still for our population parameter, that's for our slope. So for a sample, we have b naught and b1. For a population, we have beta naught and beta 1. Then notice the differences here as well in the equation for the regression line. We have beta naught here and beta 1. We still have x, but now for our y, our dependent variable, we no longer have that hat symbol over the y. And that makes sense, right? This is for a sample statistic. This is for a population parameter. So now continuing on finding the equation for the regression line, let's go through some requirements. Requirement number 1, you're used to seeing the sample of paired or XY data is a random sample of quantitative data. Requirement number 2, visual examination of the scatter plot shows the points approximate a straight line pattern. If they don't approximate a straight line pattern, it wouldn't make sense for us to want to find the equation for the linear regression line. Requirement number 3, we saw previously in 10.1, so outliers can have a strong effect on the regression line equation. Again, outliers can make a big difference in what slope and y-intercept we get, so if we know there to be outliers, we should remove those, then find our regression equation. Now, there are these asterisks here for requirement 2 and 3. We'll use those requirements 2 and 3 as stated, but keep in mind there's simplified attempts at checking a more complex requirement for regression analysis. So what those requirements 2 and 3 are getting at is that for each fixed value for x, the corresponding values of y have a normal distribution. Furthermore, for the different fixed values of x, the distributions of the corresponding y values all have the same standard deviation. If this point is violated, then in the scatter plot, you'll see points that are very close to the regression line, while other y values for that same x will be further from that regression line. What this looks like, for an example, is these points are clearly further from the regression line, whereas in example 2, these points are clearly closer to the regression line. Again, keep in mind for us, though, in the context of this class, we'll use those requirements 2 and 3. These are just points to keep in mind. So this point here, for the different fixed values of x, the distributions of the corresponding y values have means that lie along the same straight line pattern. What does this mean here? So if we have one value for x and it has multiple corresponding y values, we might see a plot that looks something like this. For this point here to be satisfied, then these corresponding y values for each point on x, the mean of those y values still has to fall along the same straight line pattern as this regression equation. So again, we go to one x value, look at all these corresponding y values, take the mean of all those y values, then plot that mean. Those means need to still fall along the same straight line pattern we see here for our regression line. But again, we'll use requirements 2 and 3. Just keep in mind they have more complexity to them, but we'll use those to see if we can satisfy the requirements for 10.2. Let's talk about some formulas now. So we have a way to calculate the slope, b1, and the y-intercept, b naught. Keep in mind our regression equation, so y hat equals b naught plus b1 times x. b1 is our slope, b naught is our y-intercept, x is our independent data, y hat is our dependent data. As I show you these formulas, try to keep in mind what the symbol notations mean. We'll also go through practice problems with each formula. So for the slope, we have B1 is equal to R multiplied by S subscript Y divided by S subscript X. So B1 is our slope for our sample statistic data. R is that measure of correlation. We can find that using Excel. Then S subscript Y is the sample standard deviation for our Y data. And similarly, S subscript X is the sample standard deviation for our X data. So that was for our slope, B1. Now for our y-intercept, or B naught, that's equal to y bar minus B1 multiplied by x bar. So B naught is our y-intercept for our sample statistic data. B1 is our slope. Then x bar and y bar should sound familiar. X bar is our mean of all of our X data, where Y bar is the mean of all of our Y data. There are some alternative formulas we can use to calculate the slope B1 and the y-intercept B naught. They look a little bit more complex here, but here's how we can calculate our slope B1 and then our y-intercept B naught. Notice that for these formulas, we need n, the number of sample data pairs. This symbol means the summation. Then both of these formulas should look close to how we calculated R previously in 10.1, where we had to pay special attention to the location of the parentheses. Do we take the summation of our X data first and then square it, or do we do it the other way around? So we practice using formulas similar to this in 10.1 to calculate that R value. But we remember we can also use Excel's correlation function to find the R value. We definitely recognize that as being more straightforward. Next, for the rounding, when we're finding the equation of a regression line, we should round our slope B1 and the y-intercept B naught to 3 significant digits now. So notice 3 significant digits rather than 3 digits past the decimal place. We'll do 3 significant digits in total. But note here, it's difficult to provide a simple universal rule for rounding values of B1 and B naught, but this rule will work for most situations. So again, 3 significant digits for both B1 and B naught. Let's go into an example now. So using Excel to find the regression equation. We're going to use the same data set we used in 10.1, where our X variable, or our explanatory variable, is the chocolate consumption, or the response variable, or our dependent variable, or our Y variable, is the corresponding Nobel laureate rate. So that table of data again with 23 sample pairs, we remember looks like this. One note here is that I am going to use 3.3 in place of 5.5. In 10.1, you'll remember I used 5.5 here instead of 3.3. So now for the examples in 10.2, I'm going to go back and use 3.3 so those data points and those values match up with the example in the textbook. So as you're following along in 10.1 and using 5.5 here, now for 10.2, go back and change this to 3.3. Previously, we used this data set. We found that R correlation value. Now we're going to use this data set to find the regression line equation. Let's start solving this now. What's the first thing we always need to do? Well, it's check the requirements. To check the requirements, we definitely need a scatter plot, so I'll remind you again how to make a scatter plot from pairs of sample data. Now we go through those 3 requirements. So requirement number 1, the data are assumed to be a simple random sample, though you may remember from 10.1, the randomness of the data is somewhat questionable. So sort of more or less here, but the data are assumed to be from a simple random sample. Requirement number 2, we examine the scatter plot. We see if the pattern of the scatter plot appears to be in a straight line pattern. We looked at the same data in 10.1. We saw that, yes, roughly, these somewhat appeared to be in a straight line pattern. Then requirement number 3, we also talked about there are no obvious outliers here, so this requirement number 3 is also satisfied. Now, be sure you're really comfortable making scatter plots from pairs of sample data using Excel. So when we do this, we want to copy and paste our data set into Excel. Remember to change 5.5 to 3.3 for all the examples here in 10.2. Then highlight all your data, go to the Insert tab, go to Scatter Plot, and always add axes titles and an appropriate chart title. What this looks like in Excel is I have all my data here. I went ahead and selected all the 23 data pairs, including the titles. So I included chocolate and Nobel, and I highlighted and selected that data. Then I go to my Insert tab here. Then I go to Insert a Scatter Plot. I'm going to click on this icon here to just plot the points. Be careful clicking something else where it automatically adds a line for you. Click this one, then you want to add in your own trend line. Once I click on this, my scatter plot should appear. Then I can click on and add different chart elements. If I'm clicked onto my scatter plot and I go to this Add Chart Element tab under the Chart Design tab, then I'll have a lot of different options, including adding axes titles. This also was part of one of your Excel assignments, so you can go back and look at those as well for more guidance. So in adding a chart element here, I go down to axes titles and I add a primary horizontal as well as a primary vertical axis title. To add a chart title, I can also go back into this Add Chart Element, then go down to Chart Title, then type in my y-axis versus my x-axis. Remember to be specific for your chart title, so you could do Nobel for your Y data versus chocolate for your X data. Next, we can add a regression line to our scatter plot. To do this, you want to click on your graph, then go to Under Chart Design tab, Add Chart Element again, then go to Trend Line, More Trend Line Options. Under the Format Trendline heading, check off Display Equation on Chart and display your R-squared value on the chart. So under that Add Chart Element button, I go to Trendline, More Trendline Options, then this will appear. You should be selected on linear here as default rather than logarithmic or polynomial, etc. So make sure you're clicked on linear. Then check off that display equation on chart, check off display R-squared value on chart. From there, you'll have your nice scatter plot, you'll have a linear trend line with an R-squared value, as well as the regression line equation. Next, I'll go through some optional formatting options. You don't have to do these, but I want to make you aware of how to do them if you'd like to. So first, to remove those grid lines that you see on the back of your scatter plot, you can click on the grid lines that are on your plot, then that'll open up a window that's the Format Plot area. Go to Change to No Line. You can repeat this for both the vertical and the horizontal lines. Another way to access this is under that Add Chart element, go down to Grid Lines, then select More Grid Line Options. What this will look like in Excel is here I clicked on these grid lines that were horizontal. Here they're clicked on solid line, but when I want to remove those, I change this to no line. Another optional formatting point here is you can change the font size of your line equation, your title, and your axes, as well as the font color if you'd like. To do this, you can click on the text box, change the font size, the color, whatever you'd like to do. After I've done a few formatting changes, this is my final appearance of my plot. I have my Y data labeled, my X data labeled, I have a chart title. I removed all of the grid lines here in the back, and I increased the size here of my line equation and my R-squared value. If you have any questions on formatting scatter plots or making scatter plots, definitely let me know. So now that I've done this, I can use this regression equation and then move on to the next steps. Some things to point out first about that line equation is the format we see for that equation. So on the scatter plot, we get a format like this of y equals our slope times x plus or minus our y-intercept. We can rearrange this to the other format we can see this equation in, so y equals our y-intercept plus the slope times x. Remember, these are the same thing. All we did is move over the placement of our y-intercept. Then we keep in mind what the y data mean and our x data mean, where the y is the predicted Nobel laureate rate and x is the amount of chocolate consumption. So to think about this equation in a different way, we could say the Nobel laureates is equal to the slope 2.49 times our x data, which is our chocolate, minus our y-intercept of 3.37. Sometimes it's nice to think about the equation in this way, so remember what is our y data, what is our x data. Then also keep in mind that this format of the equation is given as y and x. So x is fine, but we really know that y should be y hat rather than just y. So again, we see the equation like this, but we really know to ourselves this should be y hat is equal to 2.4931 times x minus about 3.37. Another important point here to make is that x is the amount of chocolate consumption, where y is the predicted Nobel laureate rate. So now for each value for x, we can get a predicted y value. So keep in mind that difference between our x and our y data. Let's continue talking about the solution now. So conceptually, we should know that the regression equation is an estimate of the true regression equation for the population of paired data. Why is that again? Remember, we had a whole population of data, and those 23 sample data pairs are just that. They're a sample from a population. So that sample data, the 23 pairs, is really an estimate of the true regression equation for this entire population that we're not looking at. We're just looking at 23 data pairs from that population. So along those same lines, this estimate is based on one particular set of sample data, those 23 sample pairs. But another sample drawn from that same population would probably lead to a slightly different equation for our regression line. And that's expected, right? We won't have the same exact X data and the same exact Y data if we selected a different sample from our population. So that wraps up this example of using Excel to find the regression equation. Remember, we made a scatter plot, then we added that linear trend line, we displayed the equation on the chart, and there we go. We also did have to round the slope and the y-intercept to just 3 sig figs total, and so we did that in our final answer on the last slide. As a reminder for our final answer, it can be noted like this, or even this way of formatting. These 3 cases all say the same thing, but remember this y value is really a y hat and not just a plain y. So now that we've used Excel, we're also going to use manual calculations to find the regression equation. For our regression equation, remember we have y hat is equal to our slope times x plus our y-intercept. That means the 2 variables we need to find are our slope b0 and our y-intercept b1. As a reminder for those formulas, the slope b1 can be calculated as r multiplied by the standard deviation of our y data divided by the standard deviation of the x data. Then the y-intercept, or b0, can be calculated as y bar, the mean of all of our y data, minus b1, the slope, multiplied by x bar, or the mean of all of our x data. So this symbol notation is written out here, so s subscript y, s subscript x, as well as y bar and x bar. Remember, for R, we can get that by using the correlation function in Excel. Let's start solving this now. The first thing we need to do, as always, is check our requirements. Because we're using the same set of data we've been using, we can consider those requirements satisfied and checked off. If you're using a new set of data, you would need to check those 3 requirements. As a reminder for calculating these, we do need our slope B1 to calculate our y-intercept B0. So that means first we need to calculate our slope B1, then we can calculate the y-intercept. So first we're going to find the slope. Remember, R we can find by Excel using that correlation function. It's the linear correlation coefficient. S subscript y is the standard deviation of the y values, and S subscript x is the standard deviation of our sample x values. Now, you can do this in whatever order makes sense to you. I'm first going to find the sample standard deviations for my x data and my y data. Remember, these are samples we're working with, so the function in Excel we need to use is equal sign stdev dot s and not p. Remember, dot s is for a sample, dot p is for a population. So to find S subscript X and S subscript Y, I just highlight all this data and I use this function in Excel to find my different sample standard deviations. The answers I should get for this are here. So here's my sample standard deviation for my X data. Here's my sample standard deviation for my Y data. So now let's continue solving for the slope, remembering that we need our R value, S subscript Y, and S subscript X. Well, on the last slide, we just calculated these 2. Next, let's calculate our R value. Now, I don't show this explicitly, but go back to 10.1 if you need a reminder on how to calculate R in Excel. When you do that, you'll want to select all of your data and use that correl function in Excel or the correlation function. What you should get for that is this number here. Now that I have all the components to calculate my slope, I'm going to do so. So I'm going to take my R value multiplied by my S subscript Y divided by my S subscript X. It's not super necessary to use parentheses here, but I'm doing so to be safe. What is important though is that we use the full unrounded numbers of the values that we can. This means that to set up this function to solve for the slope, I click on this cell that contains my full unrounded value for R. Similarly, in this equation, I also click on this cell to use this full unrounded number for my sample standard deviation for Y as well as for X. Do not round any of these individual values here to calculate the slope. Just round to 3 sig figs at the end. So again, the unrounded numbers here, then I click enter, I get this value for my slope. So I did this all in Excel. You can also do different parts of this manually with a calculator. What you'll need for that is the same formula for the slope, so R multiplied by S subscript Y divided by S subscript X. Once you know the values for all of these and you use the unrounded version, so as many decimal point values as possible, then you plug in your numbers. What this will look like is, again, as many numbers here as we can fit in our calculator. Then we multiply this by, again, this unrounded value as well as this unrounded value. You will get a slightly more accurate doing this all in Excel, but you are welcome to use a calculator. Just use as many decimal point places as possible. Then doing this, I get my same answer here for my slope. Now that I have my value for B1, the slope, now I can solve for my y-intercept. As a reminder for the formula here, we have B0, the y-intercept, is equal to y bar, the mean of all my y data, minus B1, the slope, multiplied by x bar, or the mean of all of my x data. So for this formula, we do have B1, we have the slope that we just calculated. Now we need Y bar and X bar. To do this in Excel and to find the mean of all my Y data and my X data, I can set it up like this. To start that function, I type an equal sign, then I type average, then I select all my Y data to get my Y bar value. I can do the same thing and get my X bar value as well. When I click enter here, I should get these values for my X bar, this for my Y bar. Now that I have my Y bar, my B1, my slope, and my X bar, I can now solve for my Y-intercept. So setting this up in Excel, I again copied and pasted just the values here so they could all be in the same place. You don't have to have all of your values in the same place for your personal Excel document. Here's now how I set up this function in Excel. So for B naught, I know that's equal to my Y bar minus B1 times X bar. I did put parentheses here around B1, my slope, and X bar, my sample mean for my X values. Again, I'm using the unrounded versions of these numbers. Here I have Y bar minus open parentheses, B1, my slope, multiplied by X bar, then close parentheses. I really recommend doing this in Excel so you have these unrounded numbers here and you get a more accurate answer for your Y-intercept. I click enter, then I get this answer here for my Y-intercept or B naught. If you were to do part of this manually with a calculator, we'd still use the same formula. Then you'd have to know your X bar value and your Y bar value. Again, be cautious doing this with a calculator. Use as many digits here as you can. Pay attention to the order of operations as well. So we take this B1 multiplied by X bar, then we take Y bar minus this product. We'll get this answer here of about negative 3.37. Then the last step here is to round to 3 sig figs. Remember, not 3 digits past the decimal place, but just 3 sig figs in general. That then makes our slope B1 2.49 and our y-intercept B naught of negative 3.37. Now that we know the slope and our y-intercept, we can plug those values into our regression equation. So putting this all together, we have y hat is equal to our y-intercept plus the slope times x. If you switch the format of these as well, it's the same answer. Just pay attention that we're multiplying the slope times x, then we have plus or minus the y-intercept. With numbers plugged in here, we have y hat is equal to negative 3.37 plus 2.49 times x. I apologize for the weird lighting, by the way. As the sun's setting and it's coming through the blinds, I keep moving around to try to get the best lighting. Now, anyways, if we reformatted this, it would be y hat is equal to 2.49 times x minus 3.37. We remember the meaning of y hat here. It's the predicted Nobel laureate rate, and x is the amount of chocolate consumption. What this means is that x is sort of our known value, our independent value, where y hat is just the predicted value. So what we did in 10.2 is we found that regression line equation using Excel and adding the trend line. We got the same answer then, calculating the slope and the y-intercept manually. So now we should be comfortable using both methods to figure out that regression equation. We have more in 10.2. We'll finish that up in 10.2 part 2. I hope you're all doing well. If you have any questions about the content or the logistics of the class, please let me know. I will see you next time for 10.2 part 2.